This online lecture gives you both the reactions of formation and the reactions that aldehydes and ketones undergo. Of course, we're very limited in what we're going to cover in aldehydes and ketones this semester, but there's some that we've already seen that we're going to look at again, and then there's just a couple more that we're going to look at. In aldehyde formation, you've already seen that you can oxidize a primary alcohol and form an aldehyde. Of course, you have to use the gentle oxidizing agent of PCC. You cannot use chromic acid, since that will take it down to the carboxylic acid. If you have an alkene, you can do oxidative cleavage on an alkene that has a carbon with one hydrogen on the carbon in the carbon double bond. That will form an aldehyde if you use the more gentle oxidative cleavage reagents. Ozone followed by zinc and hydrochloric acid will give you an aldehyde if you have a carbon that has a hydrogen on it. Also, if you take the alkene and convert it to a diol with osmonium oxide and then use periodic acid to cleave that diol, you can make an aldehyde if there is a carbon that has a hydrogen on it in that double bond. Okay, so this shows you the oxidation of an alcohol. If you have a primary alcohol, it will form an aldehyde if you use a mild oxidizing agent, PCC. More vigorous conditions such as potassium permanganate or chromic acid will cause the oxidation to go too far to a carboxylic acid. Oxidative cleavage of an alkene will produce an aldehyde. Notice you have to have a hydrogen on that carbon-carbon double bond. The carbon that has that hydrogen on the carbon-carbon double bond ends up giving you the aldehyde. You must use a gentle oxidative cleavage reagent. If you use potassium permanganate, you're going to get carboxylic acids on that carbon. You'll get a carboxylic acid on that carbon that has the hydrogen, because that hydrogen on the double bond gets oxidized all the way down to the acid. So how can you form benzaldehyde from benzyl alcohol? Well, the first thing you're going to have to do is write down what is benzaldehyde and what is benzyl alcohol. These are the two compounds. So you're taking benzyl alcohol and transforming it to benzaldehyde. To do that, you're going to have to use a gentle oxidizing agent, PCC. What about taking 5-methyl-6-oxoheptanal, getting 5-methyl-6-oxoheptanal from 2,3-dimethylcyclohexene? Again, the first thing you have to do is write down the structures of your compounds. So this is 2,3-dimethylcyclohexene, and here is 6-oxo 5-methyl-heptanal. 1, 2, 3, 4, 5, 6, 7 heptanal. That's the 6-oxo, and there's the 5-methyl. Well, if you look at that, you can see that's going to require oxidative cleavage. What can you use to do that? Ozone followed by zinc and acid, or another alternative would be the first step, osmonium oxide, and the second step followed by sodium bisulfite, and then the third step would be periodic acid. To form ketones, we can oxidize a secondary alcohol, and to oxidize a secondary alcohol, you can either use a gentle or a harsh oxidizing agent. The other thing we can do is to do oxidative cleavage of an alkene. A ketone is formed when the double bond in the alkene has 2 carbon chains on it. Here, to form that ketone, you don't have to really worry about gentle or harsh if you're not worried about the other side of the double bond, because oxidative cleavage will form a ketone for 2 carbons on the double bond, whether it is a harsh or a gentle oxidizing agent. So here is a secondary alcohol. and there is a ketone, you can see there are two carbons attached to this carbon. So when it's oxidized, whether it's oxidized gently or harshly, there's only one option for it to be oxidized down to a ketone, because there's only one labile hydrogen here. So you can have it be PCC, you can have it be potassium permanganate, or you can have it be chromic acid. The only thing you would have to worry about is what are the other functional groups on the compound. For instance, if there's an alkene in there, potassium permanganate would destroy the alkene. If there was a functional group that was sensitive to acid, you wouldn't want to use chromic acid. So there are times that you would not want to use these, but you do have some variability, some selection. Here's an example. This is a secondary alcohol, and so it can be oxidized down to a ketone. Notice they're using chromium here, as it can't go any farther than the ketone. Notice there's no other part of this molecule that can be changed by the oxidizing agent, so this is fine to use this oxidizing agent. If we want to do oxidative cleavage of an alkene, we can use ozone followed by zinc and acid, or potassium permanganate, or again, you can use osmonium oxide followed by periodic acid. For you to get a ketone, notice there has to be a carbon here and a carbon here in order for this to end up being a ketone. Here's an example. This can be oxidative cleavage will take this double bond right here and convert this carbon into a ketone. Now, because this carbon has two hydrogens on it, we end up making formaldehyde. And formaldehyde's relatively easy to get rid of. We can use more harsh oxidizing agents here. For instance, if I use potassium permanganate, it would have taken that down to a ketone. The only problem is, most likely, it would also start to oxidize the ketone over here. Potassium permanganate is pretty harsh. The other possibility here is to use osmonium oxide followed by periodic acid, which will give you identical results. So now practice what you've learned. How would you form 2-butanone from 2-butanol? The first thing you have to do is write down the structures. Here is 2-butanol, and here is 2-butanone. The reagent needed to do that would be to use an oxidizing agent. It would be fine to use PCC, or you can use chromic acid. To make 6-oxo-heptanoic acid from 1-methylcyclohexene, I have to write down the structures, and here they are. Now, to make these, I'm going to have to use an oxidizing agent that would take, oxidizing cleaving agent, that would take this carbon down to a carboxylic acid. The one that will do that is potassium permanganate. To make 6-oxoheptanal from 1-methylcyclohexene, you're going to have to use a more gentle oxidizing agent so that this hydrogen on this carbon here is not oxidized down to a carboxylic acid. So what do we use? Here we use ozone and zinc acid. To oxidize aldehydes and ketones, if you use chromium in aqueous acid, you're going to take the aldehyde to a carboxylic acid. Silver oxide in aqueous ammonia will oxidize alcohols all the way down to an acid also. So when we use silver oxide in ammonia, in aqueous ammonia, you end up getting a carboxylic acid. The reason that this expensive oxidizing agent is sometimes used is silver oxide, when it is reduced by the aldehyde, because when it oxidizes the aldehyde, it reduces the silver. it ends up making metallic silver. And this is very obvious in a test tube. So when you have an aldehyde and you treat it with silver oxide and ammonia, you end up making a silver mirror on the bottom of your test tube. And this is a test for an aldehyde. It's called Tollen's reagent. And when you test aldehydes with Tollen's reagent, you get a silver mirror on the bottom of your test tube. It's a rather striking and a positive indicator that you have an aldehyde present. So either of these reagents, either chromic acid or silver oxide in ammonia, will give you a carboxylic acid. You can hydrate aldehydes. To hydrate an aldehyde, you have water present, and it ends up adding across the double bond. It puts a hydrogen here and an alcohol group on this carbon. And then what happens is chromium will oxidize that down to a carboxylic acid. This is the reason that when you use chromium and acid, that it takes the aldehyde all the way, it takes a primary alcohol all the way down to a carboxylic acid. So in order to prevent that, what you have to have is no acid present, and it's even better to have no water present at all. And what do we use instead is PCC. But it is this nucleophilic addition of water that causes the formation of hydrates pretty much all the time with aldehydes and ketones when they're in the presence of water. Now, the equilibrium, except for formaldehyde, and a few other aldehydes, it's very much over toward the non-hydrate, the unhydrated aldehyde or ketone. But you have to realize that this is happening whenever you have an aldehyde or a ketone in water. This is called a geminal diol. Geminal means on the same carbon. It comes from the Greek term for twin. And so a geminal diol has twins, two alcohol groups on the same carbon. When they react with water, you can either get them, this is either acid or base-catalyzed, and the mechanism we're going to go into right now. If you have base, what happens is hydroxide is present. The hydroxide attacks the carbonyl. This is nucleophilic addition to the carbonyl because that carbon has a large del positive on it. When the hydroxide adds to the carbonyl, the electrons that are in the pi bond jump onto the oxygen, and that gives a negative charge on that oxygen, and now you have an alcohol group here. This negatively charged oxygen is then protonated by a water, and we end up getting a hydrate. Notice, these are all equilibrium arrows because this is going back and forth, and what predominates? Really, the aldehyde or the ketone predominates, except in a very few instances. You're going to have mostly aldehyde and ketone and only a teeny tiny % of the hydrate. The acid-catalyzed addition of water always starts with the protonation of the oxygen with the acid. So here it's showing the oxygen reaching out and grabbing a proton, and then the electrons jumping onto the oxygen. This protonated oxygen now enhances the nucleophilicity of this carbon that has a large del positive. That's even a larger del positive now. So even the weak nucleophile water can add to that carbon. So here it is diving into that carbon, and then the pi bond electrons jump onto the oxygen. Now we have two oxygens added. One of the alcohol groups is protonated. So you can have water act as a base and remove that proton, giving us the hydrate. Notice, the hydrate is the production of an equilibrium reaction. And so you have a very small quantity of this and a very large quantity of the carbonyl. Acetals and ketals can be formed in the same way. An acetal is the where you have two alcohols have added to the carbonyl of an aldehyde, and a ketal is where you have two alcohols add to the carbonyl of a ketone. And then there are things called hemiacetals and hemiketals, in which you actually have one of these groups would be an alcohol group instead of an ether functional group. So the first thing that happens is you get the hemiacetal or the hemiketal, and then you end up getting the acetal or the ketal.